Right, today we're going to talk about gravity currents, and there's some examples here. As we'll see, gravity currents are flows that go mainly horizontal. This is a flow due to the eruption of Pinatubo in the Philippines. It's hot fluid, that is of course, hot air I should say, which is of course less dense than the coolish air outside. It's something like 700 degrees centigrade. But there are a lot of little ash particles, and they're heavy, and they manage in this case to keep the pyroclastic flow, as the technical term is, or gravity current, on the ground, and out it comes. Now I'm occasionally asked whether this car got away from this. And what I have to tell you, because I'm an experimental scientist, is I've shown this slide for about a year a number of times. Every time I've showed it, the distance between the car and the cloud has been exactly the same. So what I can only assume is that the car goes as fast as the cloud and all is well. The cloud probably goes at 100 kilometers an hour, so this car really has quite some ability to it. Costa Rica, this is not yet a gravity current, but it does erupt. And in fact, there's a story here. I climbed up there just a few years ago with a friend of mine, and halfway up she said to me, "What are you thinking about?" And I said, "Actually, I'm praying to God saying, I'm a volcanologist. I'd love to see this volcano erupt. Could it please erupt when I get up there?" And she went white and said, "I hope you're not successful." I said, "Well, anyhow, it didn't erupt. I'm very sad." She's very pleased. I might just come back to here and tell you the truth, that this car wound up its windows, the pyroclastic flow went by and burnt partly some of the people, but they're really quite all right. Oh, and what I should say is we're going to talk today mainly about large Reynolds number flows and low Reynolds number flows, and then the next two lectures will be about flows in porous media rather than straight Euler flows or Navier-Stokes flows, and that'll be motivated by carbon storage. And I'll tell you something about climate change and carbon storage, and we'll see. Definition: gravity currents occur when one fluid flows mainly horizontal into another fluid of a different density. Mainly vertical motions, which we've already talked about, are plumes. Now I'd like to show you a video that makes a transition, it seems to me. I came across this by chance. There we go. You see what a mess that is, because it's expanded all because it's in PowerPoint. Wowee. Okay, well, we've learnt about that and there. Now, I could show you a video of an experiment of gravity currents, but much more interesting is to do the actual thing myself. And I'll say softly, part of the problem is I bet I wouldn't find the video if I looked for it, whereas this very kindly was made for me and is here. Now what we're going to do is fill it up with water. Sorry? Now, can we lift the whole thing up, do you think, the bucket?
Yeah, sure.
You can do that by yourself?
Yeah.
I'm told it leaks a little bit. I think a little bit means, I don't know. I hope you can all swim. Sorry? Okay, can we fill it up? No, don't put that in. No, that'll only make it more difficult. Oh, I would have poured it in. Okay, as you like. No, much more, much more. That's why I will use the whole bucket. I'll put the lot in. No chick, no Christmas pudding. Oh, that'll do, that'll do. Yep, that'll do. No, you might as well put the lot in. Okay. Right. Okay. Now what I'm going to do, oh, here's the gate. Put, I think, I think you'll be able to see it, I hope so, but that, can we have another one here? Right, now the old story, you have some sugar and we're going to add the sugar to this because that makes it heavier. So we have a heavy fluid going into a relatively light fluid. Now I have absolutely no idea how much I want to make it go at the right speed, but so we'll just hope. One more and that'll do it. Now we'll add a little bit of red dye so that we can see what goes on, or red ink. We'll mix it up. Sorry? It's leaking, bad luck. Thank you. Whoops. Okay, it's leaking, so let's pull it out. Pull it out. Pull it out. Right, there we go. Well, I didn't add enough sugar. But yeah, you see it's now developing and the current is going along. Now it's going, right? It's better. How fast is this all going? I want you to work it out. Give me a theory. Sorry? I didn't hear. 6. You said the number was 31. Where is he? Now it's going nicely. Thank you very much. Should I give you some money as well?
No bets.
Okay, so that is heavy fluid and it's propagating along.
We need a car
And
in there.
sorry?
We need a car in there.
I need a car. Yeah. Well, no. Well, we'll get close to that. And while 6 is not a bad answer, I want a better one from all of you. That's the best we've got so far. Okay. So that's a density current due to different densities. Now what I want to do, well, it makes no difference. Let's mix it up first. Nobody has some black ink here, do they? Oh, it cost too much. You told us that, didn't you? Sorry? Some coffee? Oh, that's a good idea. Yeah, there's some here. Thank you. Now what I'm going to do with more or less the same amount, I'm going to add some coffee. That I don't know how to put that in the equations, but just so that we can see it. What happened to this? Oh, here they are. What I'll also do is I'll add some more red so you'll be able to see it more clearly. And now, no, not yet. And now I'm going to add some heavy balls. These are ash particles. And just the right amount. Sorry? They were given to me. Yeah, he said to me they were actual ash particles. He went and collected them from Pinatubo. It was very kind of him just for this demonstration. And Ishan is going to supply you with the airfare. Is that all right? You'll pay him? Good. You can take it out of the money I gave you. Right, let's go. What we see again, it's developing Unfortunately, some of them dropped here. These are heavy. But I hope you can see that it's not moving anywhere near as rapidly as the other one. Right. And part of the reason is because it's dropped, well, it dropped many of its particles here, but now the density difference is nowhere near as large as it was. So it'll slowly go, and let me tell you, it'll stop. At some height, or sorry, some length, all the particles will have dropped out, and that's one of the things we're going to calculate. Okay, one further experiment. Well, let's put a... Yeah, oh, good idea. Yeah, if you could squeeze them up. No, if you could take them up there. Oh, get them all out. Whoa! Gee, this never happens in Cambridge like this. What I'm going to do now is add some light particles. I don't know which... oh, just the top here. Okay. So these are light particles. As you can see, they stay on the top. Sorry? They and now is well, I'll tell you what, we won't mix up the... Let's go. Take it out. Yep. Ah, interesting. Now this is an interesting problem. These light particles didn't propagate at all much. They did a little bit. And for a reason, this is a very recent experiment looking at light particles, and we've just published in JFM. I think it's just appeared. For reasons we don't totally understand, we can explain or evaluate how far they'll go, and normally they go further than this. But what we can't really understand is why they stop. Somehow they get, this is a slightly extreme case, but normally, you know, in different, we've used beads and things like that, they go out a certain amount and stop. Now, of course, I could do lots more experiments, but that's the end of the experiment, in that I could have salt and heavy particles, and somehow add some light things, some light considerable, a whole series of different combinations. Now, I hope you've enjoyed that more than that, which would have gone better, but nowhere near as interesting. Thank you very much for the books. Now, Jim, how fast was the going? No. Excuse me. I'll give you a hint. Depends on time, depends on the density difference. 6 doesn't depend on the density difference. Neither does 3.
No, those are appropriate non-dimensional units.
Sorry?
Those numbers are in the appropriate non-dimensional units. 6.
But
It's your job to tell us the appropriate.
Well, that's interesting. I'm going to put a paper into JFM saying I did an experiment and it went at speed 6. Will you be my co-author? In fact, would you be the lead author, please? Okay, now I'd like to show you some examples, some good examples. This is a compositional current in the laboratory. This is one of the first photographs taken of a laboratory gravity current. It's got salt in it. It's heavy salt water and some milk put in so that you can see it. And you see that there's a turbulent mixture here. This is definitely at high Reynolds number, probably a few thousand, maybe even no, probably not 10,000, but a few thousand. And you can see it's disturbed in the usual turbulence, and there are questions of how much the outer fluid gets entrained into it, but relatively little, but we can calculate that. Here's now what happens in Southern California almost every morning. As the sun comes up, it heats the land and makes this area hot. But over the ocean, it's not heated because there's a different reflection coefficient. And so you have relatively wet, cold air, and it's heavy, and it comes in. And we in Cambridge say, that's the intellectual fog that comes into UCLA every morning. We say it slightly differently, but I'm not going to do it that way here. Say?
Doesn't reach contact.
This is now a particle-driven current. It's heavy because of the particles due to the explosion of that building. This is in Edinburgh. And you can just see the people here behind a cordon. You can't see the cordon very well, but you can just, or I can see the people. There was one woman who thought she would be smart and get much better pictures if she was there, and she broke both her legs. Oh, no, she didn't break her legs. This broke her legs. There's, of course, another photograph I can show that's very similar to that, but I never do. It's really disturbing. This is now a hot particle-driven current in the field down a slope. I think this is in Montserrat, and you see that some of the current is actually rising because it's dropped some of the particles, just like they drop particles here, and the hot fluid is taking some of the particles up with it. This is now a low Reynolds number gravity current. This is lava coming out of in Hawaii, and I've mentioned this before, Steve Sparks measuring the viscosity. And I showed you this also. This would have been once a gravity current. It spread out for something like 312.5 kilometers in radius, and then solidified. It solidified a little bit along the way, but solidification doesn't play an important role in that. Here's another example of a problem that's relevant to gravity current flow. An ice sheet in the Antarctic, which, as you know, there's an Antarctic continent, rather rough. The ice sheet wants to spread, and it does spread in a way that we'll talk about in more detail later, and comes out into the ocean and spreads out along the ocean and then melts and causes sea rise. The first person to look at large Reynolds number gravity currents was von Karman, who went around Europe a little bit and then ended up in Caltech. And he was asked by the American military in 1940, who were going to release, or thinking about releasing poisonous gas over the enemy, what would happen if they did so, and they would do it with the wind going in that direction, but how much would come back over the American troops? They didn't want any, so they wanted to do that. So von Karman looked at that problem, and in a well-known paper called An Engineer Grapples with Nonlinear Problems, he said, look, let's consider the following. Let's look in the, what's the word? In the frame in which this is moving at velocity u, and there's a stationary current. It looks like this. We want to know what the height of this h is, given that this is density ρ1, this is density ρ2, gravity is of course down like that, and what will happen? And he said, well, I know there's Bernoulli's theorem, a half rho u squared plus p is equal to a constant. And I should be able to look at this here. This is the velocity is 0. I'll write that. Vel equals 0 because we're in the frame of this moving. So what we just have to do is to put into this equation that comes from Euler's equation. It's just an integral of Euler's equation. And what we get out of that, because the difference in pressure between here and here is ρ1 gh. So what we have is a half rho, where were we? This is ρ2 u squared. And the difference in pressure is ρ1 minus ρ2 g times h, and ρ1 is less than ρ2. Whoops, ρ1 is less than ρ2, and that's equal to 0 because the constant comes out of both sides, and I find that u over the square root of g prime h is equal to root 2. This is, whoops, put it over here. This is called the Froude number. And if it's greater than 1, then it's saying the motion is quicker than the speed of long waves on this surface. There are internal waves that are possible here, and they go at root g prime h, and so this is going faster. He was so enthused by this result, and he made such a to-do about it, that he either forgot about it or never worked on what happens if there was a wind. That was then forgotten. This is as far as he got. So that was von Karman. Then in 1968, Brooke Benjamin, I don't know why this last line turned out to be so small, but who went to a number of universities, said, oh, this can't be right. You know, von Karman's not as bright as I am. I'm much smarter, because I know that what actually happens is that this is a turbulent flow, and you can't apply Bernoulli's theorem to a turbulent flow. This is totally wrong. I'm going to do it properly. So what he did, took the Euler equations and integrated them in a slightly different way to look at the momentum. Right? So he looked at the momentum, the forces through, did it all perfectly, and got, this is T. Brooke Benjamin. He was very disappointed. Exactly the same result.
Well, isn't the Bernoulli equation simply,
Sorry?
Isn't the Bernoulli equation simply an integral of the momentum balance?
Sure. So, yeah, you're quite right. Why was he so surprised? I have no idea. You're quite right. There are two different ways of approaching. They both obey the Euler equations, different integrals, but yeah, just exactly the same. So he was very surprised, very disappointed, especially that he got root 2. He wanted to get something different, but it's just not possible. The other thing which I don't think Brooke really realized is you've got u, you've got g prime, and you've got h. This is Lt to the minus 1, this is Lt to the minus 2, and this is L. There's only one rule and there's nothing else. There's no, so that's the, you don't have to know about anything, really, to get that this is at least equal to close to 2. But Brooke, I don't know, he got very excited by that. Now, so what we're going to do is to look at the problem. Oh, I should have said it makes no difference because this is considered to be small density, whether we have a light current going on the top or a heavy current going on the bottom, Busenesque. So von Karman in 42 got root 2, Brooke Benjamin in 68 also got the root 2, very disappointed, and John Simpson and I in 1982, I think, made some measurements and found that in actual fact it's 1.19, which is not very different to root 2. Now, but how do we get 6 out of this? How do we see how quickly it ought to go? Well, of course, what I'm going to say is dimensional analysis. What we want to do is find the length of the current as some function of time.
When you say you mean how the contact line moves? Or?
Well, the idea is if we're in the frame that you see there, this whole thing moves at one velocity u, and then we're in the frame so that that's been made steady, and so for the evaluation, the velocity comes down like this and goes in here.
No, that's not when you're taking measurements, then you're looking at the contact line motion, right?
Yeah, you're looking at, if you like, what the contact line is moving. Yeah. So what we have is that L, we're going to use, yeah. Yeah, technically it's not a contact line. You don't use surface tension. but it's a line of contact. And of course, in actual fact, it doesn't go like that. What happens is it bends a lot like this is a simplification. But what we're going to do is use dimensional analysis. So we have that the length of the current, or as I've called it xn here, the x position of the nose, is going to have to be a function of g prime and time. What else? Well, it clearly is going to depend on how much stuff I put in here. So it's how I start it. We could say the initial length and the initial height, but let me cheat a little bit or say, look, it's more likely it's the area. It's the area that's conserved. So I'll just write down the area with a little question mark. I mean, it's correct, but a question mark because you might not see that. Now, dimensions. Okay, LT to the minus 2, L squared T, and, sorry?
Which area?
Oh, the cross-sectional area. So the area would have been the fluid that I let go initially. From this side, yeah. I mean, everything is two-dimensional in this experiment. Now, I'll tell you what, let me cheat a little bit and put this as the velocity rather than the length, because I remember the answer here. It must depend on these parameters. Okay, well, I wanted to have dimensions. What's going on here? I wanted to have dimensions. No, I was right in the first place. What am I doing? I wanted to have dimensions of a length. So let's start with a to the half. That's terrific. And then I've got a length. And then I could get a function of anything that's non-dimensional. But it's already clear there are only two variables here and two parameters here. I don't know quite what to call it. Sorry? 2 units here and 3 variables. So clearly I can make a non-dimensional one. And I'll put A over G prime squared. And then I have to put T to the third. Yeah, and then I C to the minus 3. T to the sorry? L squared T minus 4. No, it's T to the 4th. Okay, that's non-dimensional, right?
I think so.
Minus 4 was right.
Sorry?
Minus 4 was correct.
Yeah, it is correct. You're dead right. You know, I did this twice this morning just to make sure, and I did it with no effort whatsoever. Maybe that was the problem. I should have spent a lot of time doing it. Okay, so now I've got this. How am I going to get the function? There's just no way of getting the function from dimensional analysis. So while this is correct in some sense, gee, this chalk is hopeless. Correct in some sense, it's useless. You can't get the result with dimensional analysis. You have to do some solutioning. Proper solutions. And there are 2 ways that you could get the solution. One is to write down the equations and solve them, and we'll do that in the next slide. Here's a simplification, which is to say, look, I know it's not a good exact physical representation, but it should be good mathematically to say I start with a rectangle and I end up with a rectangle of length xn rather than L that increases and it has a height h. And so my conservation equation is going to say it stays at the same area, xn times, and the final condition that I got here, that dxn dt, i.e. the velocity, is the Froude number times g prime h to the half. This is called a box model. And what you get out of that is that it's got to look like this. And I guarantee you it'll look like that. The function is, you work it out. 8 over 3, the argument 8 over 3. Okay, now some people don't like these. Yeah.
How do you get the right-hand side? Froude number is a function of g?
This here, this is a constant, right? And now I go in here and I say h is a naught over xn. So I have a differential equation that's basically xn to the half dxn dt, and that's where I get the...
How do you write dxn by dt is equal to
This one.
Oh, because that's what this is.
You do a macroscopic momentum balance in the box. That's all you do.
Sorry?
Macroscopic momentum balance in the box gives you that.
I'm sorry, I didn't hear the beginning.
Macroscopic momentum balance in the box gives you the formula.
Yeah, yeah.
Velocity.
If you like, yeah. That's either Bernoulli or momentum flux or whatever. This has to be the condition at the front. And so I'm using that condition at the front. That's what this is. And this conservation law. Yeah, Ishan.
What is the basis
Oh.
for it? What is the basis for assuming that the crude number is constant at the front?
What else could it depend on? Well,
It could depend on any other non-dimensional number. For example, a t to the minus 4 divided by d prime squared.
no, but that's not what you get from simple relationships like this and the momentum balance. So if the Froude number varied, then that wouldn't...
That's not a steady flow. And, it's an additional assumption, right? It's not a foregone conclusion.
I think it is, because that's the only thing that's consistent with this integral of the Euler equation, which says that you get this, or the momentum balance, and it says you get this is equal, well, you get that equal to a number. So there's not anything else it can depend on, and obey the equations.
You just said it is meant for inviscid.
Oh yeah, sure. It's definitely true. It's inviscid. It's high Reynolds number. I'm not allowing viscosity, and it's also assuming it's a thin layer. Yeah, but
Bernoulli's equation is for steady state. This is not steady.
no, it's not for steady state. No. The Bernoulli's equation is not for steady state. I can add d phi dt plus here, but there isn't a variation here, because far upstream the velocity is uniform in this frame, and the idea is that this is uniform too. No, I think this is all you can get and solve the Euler equations, but I will back off a little bit, but not with a lot of pleasure, but we'll do it to say, experiments say that this is always true, no matter what size you do, or, well, as long as viscosity isn't important or anything like that. And of course, again, if you rotate it, then things are totally different. So this is
Isn't this equation for dx dn, isn't that simply making use of the definition of capital U?
Yes.
So that's not a momentum balance. It's
oh no, but this is the momentum balance.
okay.
Yeah, this is the momentum balance, and then I take this, and then I remember what Brooke Benjamin found, and I write it here. So this is a box model, very simple, and some people object, because I use box models a lot, and when they object to me, I let them finish, and then I say, we're talking about processes that happen in volcanoes and in the atmosphere, and I've never seen a gate in the atmosphere lifted up and it go along. Okay, this is a simple model. The gate is an artifact. I think that's worthwhile. But we could argue that, and I have argued that with a few people. What we can do instead is to write down the mass equation and the momentum equation. We've written these before. This is the momentum incorporating the mass equation. And you can get a similarity solution this time. You write down the height as a function of position and of time, so it's not a box model. You're allowing variations in terms of this capital H of y and the velocity in terms of this u of y, and you get this. You've got to get this. You've got to get this. There's no room for maneuver. This is slightly different. And this is slightly different. There's no doubt the h has a variation with y. And I think I included a graph, didn't? No, I didn't.
What is y?
Y is this non-dimensional x over xn. So what we're saying is that h, which starts at a value, looks like this. So it's definitely not a box model, and the velocity looks like this. So this is the velocity, this is the height, and this is x over xn. And xn, of course, is a function of time. So it's a similarity solution that increases with time, still goes like t to the 2/3, it still goes like this, and this value is pretty close to the number we got before. And if we're going to say that the Froude number might change in some situations, who cares less, in my opinion, whether it's that or the box model. Okay. Next, I want to talk about is the effects of a mean flow, which von Karman was asked to do, but didn't. And we did some experiments, and I'll show you some theory. We put in heavy fluid, and we let it spread, and there is a flow. This is basically a flow tank. I think it's clear that this is only going to go a certain amount upstream. And what you want to know is how far upstream it'll go, i.e. where do you station the American troops if this is gas, so that they're out of the range. I'm not going to go through the details here, the mathematics, but let me just tell you the results. And somehow on my slide this morning this got all muddled up. So this is the maximum non-dimensional upstream distance. So the maximum upstream distance, non-dimensionalized with respect to LP, where you have this now, G prime, well, I've already talked about G prime, the initial concentration of particles, the initial area, and, oh, this must be, oh, damn. This, sorry, no, I've put this out of order. This is for particles, actually. Oh, one second, am I mixing up two? I'm sorry, I may have mixed up two different. I'm sorry. We calculated how far it went up, and this is for particles. Somehow I've got the wrong graph here. Yes, I see here. I'm terribly sorry about that. Sorry?
VS is the Stokes involved?
Yeah, VS is the Stokes. This would be the right result if there were particles that were falling out. I'm sorry, I somehow pulled the wrong graph up. Because there's almost exactly the same graph. I'm terribly sorry. Okay, now here's the particle-driven flow that should have come here. Well, you've seen this sort of thing before. This is actually in Unzen. You can get the size of the scale. You can't see very clearly, but there's a hotel here. Sorry, there was a hotel here. It doesn't exist anymore as this flow came by. Here's another very important one of Mount St. Helens. Particle driven because it's heavier than the surroundings in the gravity current, but it's hot. And the thermal temperature, well, what else? The thermal effect is to lift it up, to make it buoyant. But the particles win until it comes to this point here, and here the particles drop out. Or have dropped out all the way along, but here's as far as it goes. The density now is equal to the density of the atmosphere, and it rises as a so-called coegnate bright column, but names don't matter. But apparently there were people here who were taking photographs, and they were killed, and there were people here, including one guy whose wife apparently said, "You're going to be killed, you're going to be killed." He said, "No, it'll be all right, it'll be all right." And up it went. I think it was just a complete fluke. He was very lucky. Yeah, he said 6, and somehow that was sufficient. Well, here's now a particle-laden gravity current down the slope that's been caused, we say in Britain, by the Prince of Wales skiing by here. You know, he initiated an avalanche once. I was once hiking in Austria with my wife on a glacier like this, and a current like this came down quite a few hundred meters above us, and she panicked and said, "Herbert, move, move, move." And I said, "We don't have to move. either it'll die out, in which we'll be fine, or it'll sweep us, which there's no point in moving. Said, oh, you damn mathematicians, why do I have to get involved? Well, as you can guess, it did die out. Otherwise, I wouldn't be here giving the lectures. And the question is how far it goes. Well, here's another example in Montserrat in the West Indies of a particle-laden flow going down a slope. Now, I want to, maybe we should have a 5-minute rest here. Okay, 5-minute break here, and then I'll tell you about this.
You have no pictures of mudslides in California?
Continue to talk about heavy particles that are falling in a turbulent medium. How rapidly will they fall out? That's what you want to know. And the idea is that they're turbulently mixed here. They're held in suspension, if that's the right word to use, held in the liquid. But on the boundary, it can fall down here, and because there's no turbulent velocity. So the number of particles that will change with time t is the Stokes fall velocity times the concentration at the boundary, this being C of naught. So, well, but the particles are almost uniformly distributed here. So you can work out what the particles are at the top of the boundary layer if you want to, by saying the concentration has to be the number of particles divided by that height. So you've got n dot is minus v and C of naught is n over h. So that says that the number of particles and the concentration should go down exponentially, and the time scale is h over v. Okay? This was apparently, here we go again, Einstein did something like this. Forgotten McCabe's first name. No. Well, Nick McCabe. And then Martin and Noakes looked at this very seriously, and what they did is they set up a situation like this, mixed the particles, and took photographs at different times, and then counted the number of particles. That's not quite true, because one of these was a professor and one was a student. Guess who did the counting? Of course, the professor. Anyhow, they got a line like this in in logarithmic axes here, showing that this is quite right.
So they stir it up initially. So what sustains the turbulence?
What's that?
What sustains the turbulence in this case? If they stir it up.
Oh, no, you're quite right. It was sustained turbulence. You're quite right. Quite right. Yep, it was sustained turbulence, and it agreed very well. Now, just as an aside, and there's, I think, something to be said here. I think it's fascinating in some sense, or crying in another sense. I helped them quite a bit in this. I did most of the theory for them. They did the counting and the experiments, and they acknowledged me very kindly at the end, saying that I'd done the theory. Then about 3 years later, I put in a grant proposal to look at something in which this was involved, and I made a mistake, there's no doubt about it. I forgot to include the Martin and Noakes reference. I knew about it, but I forgot to include it. So one referee wrote back and said, this guy knows nothing about the subject. He clearly has never read Martin and Noakes. Didn't reference it. To which I did reply to the grant proposer, or the grant officer, this guy knows nothing about the subject. He hasn't read the paper, because he would see that I'd helped a lot. But anyhow, I didn't get the grant, which I was annoyed about, partly because of that. Yeah, that's the important part. So don't forget your friends. Now I'm going to say a few things without proving them, but hoping that they're useful. We're talking about surges flowing down a slope, and what's going to be important is the Stokes fall velocity of each particle, what the angle is, and we want to know what the run-out length is. What is this? I don't know what's gone here. Something's missing here. Now, what you can say from dimensions in this case, it's got to look something like this. Somehow you can never get the angle, of course, but the free fall velocity comes in with the due prime. It's different to this one that I've told you. You can write down the governing equations, and you find that this function is proportional to this argument. And you can't find what the function of theta is. That's you have to work out, and you do that numerically, let's say.
The friction of the
Sorry?
the friction.
There's no friction here. We just imagine the particles are going down, but they're falling out. And so the density that's driving the flow is being reduced as the particles fall out.
You have drawn it at an angle. I'm wondering
Yeah.
whether the friction with the bases has to play any role.
I'm sure there's a situation where the friction will play a role, but that's
I keep thinking
not.
of landslides.
Sorry?
I keep thinking of landslides. And
Well, you know, if I tip this up, except for making a mess, I don't think friction would play much of a role.
well, it's mostly through the
Yeah, now I want to say something about viscous gravity currents. Here we have a typical, and we'll make it two-dimensional current. There's high pressure here because of this heavy fluid here, low pressure here because there's less of it, so it spreads here with a velocity profile that's parabolic, 0 at the wall, 0 shear at the top here, and the vertical gravity induces a horizontal flow because of this variation in pressure due to this height. The pressure gradient causes the fluid to flow, and it's resisted by viscous stresses. So this, you know, y is now upwards, y is 0, y equals h of x of t, which we don't know, we want to find out. dp dy is minus rho g, that's just the hydrostatic approximation. We integrate that, and that tells us how p varies with x, because dp dx is rho g dh dx. We don't know what h is, but we can evaluate that. dp dx is related to the shear mu d2u dy squared. We only have to consider the y component because it's a thin region that's spreading. That gives you this velocity profile, 0 shear at y equals h, 0 velocity at y equals 0, and that gives you the flux in terms of h by this relationship. Now, as I think I said before, if you have a different flux here than here, that can only be accommodated by a change in height. So you know the flux here, and that difference has to be taken care of by a change in height. This is, if you like, flux conservation. That says that dh dt is minus dq dx. So you get the nonlinear partial differential equation. H cubed here makes it nonlinear partial because it depends on x in these two dimensions and on time. Now, in this case, where it's going in two directions rather than the axisymmetric case I've talked about before, from 0 to xn has to have half the volume, and always has to have half the volume. So that's a constraint that needs to be added. We non-dimensionalize as suitably with the thickness and a time to balance those, and that says that the length has to go like time to the 1/5, and the thickness will go like time to the minus a fifth. It gets smaller and smaller as time goes on. This is now, I've shown you this slide before. This is for an axisymmetric case where what was written as ddx we now have as ddr. And just to repeat what I said before, here were some experiments I did. Alpha equals 0 means it's constant volume. Alpha equals 1 means it's constant flux. And here's the relationship for constant volume. It goes like t to the 8th with this constant, and you see it agrees very well, and also constant flux agrees very well, and you can get this solution for any value of alpha you like. Here's just an example of the domes on Venus. I think I showed you this, and my friend Dan McKenzie was involved in the so-called Magellan expedition, and he said, these are just like Huppert's gravity currents, and he chose my scale of how it should vary in the axisymmetric case. Everything is axisymmetric here, and here are the data points from the Magellan, and here's my eigenfunction, if you like. And part of the reason Dan did this, as always, there were two groups that said I didn't know what I was talking about, I was totally wrong, I hadn't taken into account the solidification and the non-Newtonian effects, and I said I don't think that plays a role, and their predictions were nowhere near Dan's theory. I'm sorry for my name up there, I got it from Dan, otherwise I wouldn't use it.
How did you solve the equation?
Say?
How did you solve the equation?
No, you just do it by similarity form of solution. Yeah, it's all similarity.
Sorry, I missed the Venus. Are those are time-dependent fluids?
Say?
They're time-dependent fluids?
Well, well, we assume that what happened, because we don't know, really is that the volume, which is the final volume, came out more or less instantaneously, and then how would it spread? What would it look like? So it would look like that. Now, this is a video made by Roy Saag, a visiting postdoc from Israel. This is going to be Newtonian syrup that's going to spread just as I did before and axisymmetrically, and you'll see it goes just like t to the 8th. You'll be able to tell that. And here's a non-Newtonian, very non-Newtonian fluid called xanthanon. And let's see if I can get both movies started at the same time. Oh, damn it. What's going on here? There we go. Well, I couldn't get them to get started at the same time. But the point I want to make is that there's really not much difference. If I'd only started them together, it would have looked more similar even. And you have a plan view there. Okay, the next slide says, look, here's another application, and I've sort of mentioned this before. Here's an ice sheet, and because of the pressure difference due to this free surface, the ice sheet flows out into this direction. It flows along the bedrock, or has contact to the bedrock, but it's light. It's less dense than the ocean. As you all know, ice on top of drinks floats. So that means eventually at what's called the grounding line, it has to leave and comes up here, and then it'll melt. You get icebergs. Now it's true that ice is a non-Newtonian fluid, and that no doubt involves other aspects, but the simplest case, and the one that I've done, is to consider it just as a Newtonian fluid. I was going to say one other thing, I've now forgotten. Oh yeah, this grounding line must depend upon the snowfall. And we know how the grounding line has changed over the last millions and zillions of years, because we can see that from geology. So what I hope to do, but I haven't yet got to it, is from the data in the grounding line, work out what the snowfall will be. That's a problem. Oh, that says it's the grounding line. Now here's an experiment. This one starts by itself. Some relatively light syrup being put into this water down the slope. Wonderful summer student, Rosie Robson. And it takes off at the grounding line, and you see the grounding line moves down a little bit. It has a variation with time, but eventually it'll come to a steady state, and you'll just have a situation like that. And off it goes. Now, that suggests, what about looking at a grounding line, because that's actually what happens for a non-Newtonian fluid. Well, here's a Newtonian. I only press this once, don't I? Oh yeah, no, twice. Here's a Newtonian case. We're putting it between two plane light fluid. It comes in here, and there's a grounding line, and it takes off and goes like that, and it's pretty axisymmetric and nothing surprising at all. Here now is the same fluid before, the non-Newtonian case. It's not axisymmetric, I guarantee you that, as you can see. So in the grounding, the grounding line for a non-Newtonian fluid is really quite different. And I don't think we totally understand why that happens, but it forms a really very complicated structure, quite different if it was just a Newtonian fluid. And there's no doubt that ice is a non-Newtonian fluid. We simplify. Sorry?
The blue fluid you're injecting is the non-Newtonian fluid?
Yeah, it's the same xanthian.
Surrounding medium?
Surrounding it is water.
So they're flowing into a Newtonian fluid, but
Yeah.
the fluid injecting is non-Newtonian.
Correct.
Solution.
Yeah, seawater is pretty Newtonian. So,
Xanthan gum has a real extensional character.
sorry?
Xanthan gum has a real extensional character.
Yeah.
What's happening when it's coming out of the nozzle.
Well, now here's a question.
It's rod-like, yeah. So they get oriented when they come out of the extensional velocity.
We're asking for it to.
It's a very
Big.
very non-Newtonian extension.
Yeah.
That's why.
And now this is just a point. Here's an ice tongue in Antarctica, and here's what we can produce in Cambridge. They're similar.
What material are you using here?
The xanthian. That's a well-known, isn't it, non-Newtonian fluid, and this is ice. Well, it's more difficult than I've indicated, because in some parts on the west of Antarctica, the bedrock, yeah.
Sorry, you showed an experiment earlier where you said that the difference, or rather you showed for the gravity current,
Yeah.
the difference between Newtonian and non-Newtonian did not matter.
Yeah,
And now you're saying it does matter for something.
for some things. So what I'm saying is, if I have the simple gravity current of just releasing the fluid going along a plate, it doesn't seem to make any difference. If I make it go into heavy fluid, it'll first go along like that, and because the fluid is heavy, it rises, and that seems to make a difference.
So even
Do I understand why? No.
so in both there is some sort of a grounding line.
Well, I wouldn't call that a grounding line. I know what you're saying. Well, in one case it's propagating like this, and the other case is propagating like that. This is propagating, you know, there's a difference here because of the density. So this is what happens in real life. You see there is a grounding line, and and this is an extension, but this is hardly a flat surface. And there's an interesting question of the simple experiment that I did for you last week of the spreading dropper that I've shown here. What happens if it's over a corrugated surface? What if, for example, it's statistically corrugated in the sense that there's some statistical distribution? Might it come to some point that's so high it can't get over it? Again, problems that have not been looked at but more or less talked about. This is another sort of gravity current of the eruption of Tal in New Zealand, where there was a volcanic eruption. It produces a plume, but there's so many heavy particles that the whole thing has fallen down, and then it spreads. And now the interesting thing is, The greatest eruption in Tapo was something like 100 AD or something like that. And what you know is what the distribution of sediments is now, some 2,000 years after it's happened. Making, without doubt, some simplifying assumptions, can you do the inverse problem? Backtrack what the eruption must have been like, how strong it was, how far it would go. I think that's all I wanted to say today. Next time we'll talk about climate change and carbon storage and flows in porous media. Okay. Thank you.